Okay. So what we're going to be covering here is going to be pretty quick, I think, I hope. Is going to be sections 5.3 and 5.4. 5.3 I covered a little bit in previous classes, but it's worth reviewing. So some of the terminology that I need to make sure is clear, and you should read these sections because they're very important. So in section 5.3, you're going to go ahead and see some terminology, such as x.low. What that means is x is an active low, and it has a relationship to what you would consider a normal signal, which is x.high, except for that it's x.high bar. Now, these two have this relationship and they're inverted, right? So x bar dot low is equal to x dot high. This is roughly equivalent to, well, really functionally equivalent to having an inverter, right? So let's start with a problem where this can be seen as to why it's useful. So if f is equal to this, throw down some bars. All right, we can start looking at the inputs, and the goal is to develop a circuit off of this, right? So let's go ahead and take an OR gate, right? So top level gate is going to be this OR gate because I have two terms ORed together. And let's say that I want an active low output. So F is active high by default. So I need a low, active low. And you just do that, as I said, by adding a bubble. This is now F dot low. Okay, see that? Normally this would be F coming out of the OR gate. Now it's low because it's inverted. Alternative, yeah, anyways. So now we know that these are going to go into these AND gates. And we can start by labeling what they're going to be. I know this needs to be A, not A and B. And this needs to be A and B and not C. So there's going to be a 3-input AND gate down, or sorry, AND gate down here, and a 2-input AND gate up here. So one of the things that you can do is just connect this straight up. It's done. It's done. But we need to make these inputs work for us. What if we have active low inputs? Let's add a bubble. Let's add a bubble. And we're going to have A bar dot low and B dot low. Right? So I have bubbles. They're inverted. Now the nice thing with doing it this way, you see I have an universal gate in the NOR gate and the alternate form of the NOR gate, right? Because this is functionally equivalent to this. We can do the same thing here. Oh, there's supposed to be 3 inputs with another bubble. And we can do the same thing where we can do A, B, and C bar dot low. Oh, because I have inversions here, inversions on the input. Done. Nice and simple. Now you can remove the A bar and C bar by having A and C and then throwing an inverter into it. So if you had a more complex expression, you can cascade all of this into more and more gates if you need it to. So let's look at another example. Actually, let's reuse this example. So there are 2 ways that I'm totally fine with you designing circuits. One of them is, so this is the way the book does it. The way I do it, I always just call it bubble pushing. It might have a better name. But we do the same thing. You always start with an output gate. Now the next step is, I'm going to do, for this one, I don't need an active low, I want an active high. But I still need universal gates. Now my starting gate is an OR gate. It is very easy to turn this into a NAND gate simply by adding inverters at the input, right? Because of the functional equivalency. But I need to add additional bubbles. So I know that I'm going to have 2 AND gates out here. and one of them is 2 input, one of them is 3 input. And I'm not going to do anything fancy with the inputs on this example. It's just going to be A bar, B, and A, B, C bar. Okay? But to connect these up, so I've added bubbles here, and that's problematic because I've changed the expression. But I can undo an inversion by pushing a bubble to each of these. Right? That's why I say bubble pushing. So I basically take a bubble here and a bubble here, and then I just push it down the line until it runs into a gate. Now you'll notice if you have this type of term, we call this the sum of products, because I have a product, and I sum them together. So sum of products. This type of term will always easily allow us to design a NAND gate circuit, because I will always have an OR gate that I can turn into a NAND, and I can push the bubbles into the AND gates and also turn them into NANDs. Done. F. Now what's interesting, still, I have universal gates. If I need an F.low, I just throw an inverter. Right, which I could draw as a bubble, but then it's a little unclear if this is a universal gate or not, so I like the explicit inverter, which looks really funky on the way I drew it, but it is what it is. So you can do another example where you have A or B, C. Let's make it a little fancier, right? Not. It's very difficult to draw circuits when you have a not term over a large segment of it. So we can go ahead and simplify this into A bar and B bar C. Right, that's just a Morgan's. We've done over that in previous video. It's not that difficult. Hopefully it's not that difficult, right? I just converted the plus to an and, so or to an and I inverted each of the terms. So one term was A, so it went A to A bar, and this was not BC, was a whole term, and it's now barred. The issue is now I have another term with a big bar over it, so I keep the A, I do and B, C, bar, right? Because it would be B double bar, but that just cancels out. Oh, and we need to change this and to an or. And with that, I need parentheses. Done. Simple expression. Now you can see that my main gate is an AND gate. Let's start over here. I'm starting with an AND. Now the two things, if I need an active low, I could add a bubble and do it like this example, which I recommend you try. Or I can do my way, which is a little bit interesting in this one. That's why I kind of like the bubble pushing in this. So in one case, we're going to have an A. And in another case, we're going to have an OR gate, right? That's coming from the B or C. Well, B or C bar. Boom, circuit's done. But I need universal gates. What do? I push a bubble here, and I push another one all the way along to the A. But the A doesn't have a gate, so inverter. Done. This side, bubble here, push one along the wire, boom. All right, so here we have a NOR gate, and here we have a NOR gate. Universal gates, done, solved. I recommend doing the example 5.2 on the walkthrough on your own time. It has the examples. So give me 2 seconds while I look at 5.3 to make sure that I haven't missed anything that would be considered important to you guys. Okay, so in 5.3, it's going to talk about incompatibilities between the logic levels. I recommend reading that. Again, this video is supplemental for examples and walkthrough. I'm keeping it short, so it's not a full replacement for reading the chapter. Specifically, right inside of 5.3, there's a logic circuit design progression that has steps 1 through 6 that you should definitely read. I did kind of the shortened version of that. So now if we march on to 5.4, which is logic analysis. Now, that's just going the other direction. So logic design is where we make a circuit, and logic analysis is where we take a circuit that someone else has designed and attempt to understand it. And these circuits can be fairly complicated and frustrating to understand sometimes. But fortunately, the analysis is pretty straightforward. So let's start with a new page. And if we're going to go ahead and look at figure 5-11. So I'll just pull that up this way and zoom in a little bit, if I remember how to zoom in. Okay, so here's the circuit, this 5-11. The first thing that you want to do when you're doing analysis is explicitly label your nets. So that's what we see here. Is this net is labeled as A or B. Well, let me back up. It's in design, you always start with the output gate. In analysis, you always start with the input. It's because it's difficult to see exactly what the output is until you've built up to it. So here we have an OR gate, and you have A high and B low. Now that's a little bit obnoxious, but you can just write it as A or B bar. But there's an inverter here. That seems a little bit odd, doesn't it? Because you have B low tracing through, and they've written it as B bar low. And A traces through and stays A.